Okay, all right. So what we'll do today is continue discussions on the neutron star mass and radius, and then I will discuss what we've learned from observations. After that, I will discuss, what we think are possible phases of higher density matter in the neutron star core. And I don't know if we will have time to also talk about supernovae, but let's see how this goes. And I just heard that this will be the last lecture, so there are certain topics that you will have to come back and look online for lecture 4, and I'll try to provide that to the organizers within the next day or two. Okay, so we have been discussing various layers of the neutron star, starting from the outer regions. We talked about the outer core yesterday, and we'll continue discussing this. Yesterday, we talked about the structure of a neutron star. We started with a very simple estimate for the radius of a neutron star, just based on the minimization of the gravitational energy and the energy of a degenerate Fermi gas of neutrons. And that already gave us some insights on, how does the radius change with mass when neutrons are non-relativistic, and what is the typical order of magnitude for the radius of the neutron star. And that's what's shown in the first line there. And we also discussed that if we want to calculate the structure of neutron stars in some detail, we need to solve the hydrostatic equilibrium of a neutron star. And because neutron stars are very compact, the effects of general relativity need to be accounted for. And the equation that allows us to calculate the size of a neutron star is called the Tolman-Oppenheimer-Volkoff equation, which is written in the slide here. And you can see that once you specify the energy density and the pressure of matter, you can solve this first order differential equation quite simply and calculate the mass radius relation. So one interesting feature which we were talking about at the end of last lecture was that if you assume that neutrons don't interact, this is what Tolman, Oppenheimer, and Volkoff assumed in 1939, you end up getting neutron stars whose masses and radii are related by this black curve shown here. And we discussed that this is clearly a problem because the maximum mass of a neutron star made of non-interacting neutrons is less than 0.8, but we see neutron stars that are much more massive as, say, 2 solar masses in nature. So that's clearly giving us important hints that there must be very strong interactions between neutrons in the neutron star that can provide the pressure needed to support these more massive neutron stars. So in this figure, we plotted the mass radius relationship for models that include nuclear interactions. And these are a bunch of models. We discussed that the red curve is obtained by just including 2 particle interactions or 2 neutron interactions using a potential model. And then the 3 particle interaction between neutrons provides more repulsion. So when you go from the red curve to the green curve, you have more repulsive interactions and hence more pressure that allows you to support more massive neutron stars, as shown by the green curve, which now intersects the 2 solar mass line. If you increase the 3 neutron interaction even to larger values, then you can get larger maximum masses, but it also increases the radius of the neutron star. So you can think about moving from the red curve to the black curve by just increasing the strength of repulsive interactions in dense matter. We also discussed that to describe interactions between nucleons in a systematic way, we can only do that up to a density of about 2 times nuclear density. So to a very good approximation, we can only calculate the equation of state up to a density that's equal to 2 times the density of a nucleus. That's 2 times rho 0. And you can see from this curve that we have to really extrapolate to much higher densities to describe these neutron stars. So that's what we'll talk about today. And before we talk about these new phases that can appear at high densities, let's see how far we can get without being very specific about what sort of matter exists at very high density. So again, there's a very simple one-to-one correspondence between the pressure as a function of energy density, which is shown in the left, and the mass as a function of radius. So this feature is what we use to learn something about the pressure energy density relation by observing neutron stars of different masses and hope that we can reconstruct the pressure energy density curve if we know the masses and radii of a few neutron stars. So for example, imagine that you had two different equations of state, one equation of state shown by the red curve and another equation of state shown by the yellow curve. So the red curve has higher pressure at lower density and lower pressure at higher density. Now the type of neutron star it makes is shown on the right panel. If you compare it to the type of neutron star made by the equation of state shown by the yellow curve, you see some interesting differences. So if you have a lower pressure at smaller density, the radius of these lower mass stars is smaller. But because you have a higher pressure at larger density, the maximum mass of a neutron star is increased compared to the red curve. You can think about another possibility where you have an equation of state that has a lower pressure at higher density. If you have an equation of state with a lower pressure at higher density, it would make neutron stars with smaller maximum masses. This is what we also saw when we were comparing the ideal neutron gas equation of state to the interacting neutron gas equation of state. So a very simple conclusion we can draw from the correlation between pressure as a function of energy density and mass as a function of radius is that if we observe in nature that the radius of neutron stars is small, but their maximum masses are large compared to, say, one solar mass, then it has a very specific implication for the properties of high density matter. It says that there needs to be a very rapid increase of pressure from the relatively low density regions to the high density regions to be able to support these observations. So this is something that we are actually finding now in nature, and I'll discuss that more in detail in the next few slides. So let's look at the pressure as a function of energy density very closely so that we can understand which part of the equation of state affects the radius and which part affects the maximum mass. So what's shown here is a curve. The white curve here just indicates pressure. This is the log of the pressure as a function of the log of the energy density. And this at about 10 to the 6 grams per centimeter cube, the electrons become relativistic. This is the outer crust of the neutron star. We discussed at about 10 to the 11 grams per centimeter cube. That's the density at which neutrons drip out of nuclei, and that's the inner crust. That's the beginning of the inner crust of the neutron star. And at about 10 to the 14 grams, you make a transition from the inner crust of the neutron star to the outer core of the neutron star. Now, as I discussed, there are regions of the neutron star we can calculate. That's shown by this, the red curve separates the region where we can do reliable calculations from the region where we don't have tools to calculate the equation of state very accurately. So there are lots of speculations on what can exist. For the first part of this lecture, let's ignore these speculations and just see whether or not we can learn something about neutron stars by just using calculations in the lower density region shown to the left of this red curve. So a lot of work, mostly based on effective field theory and quantum many-body theory, has gone into calculating the pressure of matter at nuclear saturation density. And that's shown by this error, by this point, red point with the error bar. So at 10 to the 14 grams per centimeter cube, the error in the calculation of the equation of state is surprisingly small, because at these densities, we know that two nucleon interactions dominate, and these two nucleon interactions are very well constrained by data. And this is also a density region in which the hierarchy of many body forces we expect to converge very well. So for all of these reasons, at 10 to the 14 grams per centimeter cube, the equation of state is very well known. Now, as you go to 2.5 times 10 to the 14 grams per centimeter cube, that's the saturation density, you begin to see that the error in the pressure begins to increase, because in a low energy effective theory, as you go to higher densities, you explore nucleons with larger momenta. And because these larger momenta mean that you have to take higher order terms in the effective theory to describe the pressure, and that begins to increase the uncertainty in the pressure. So at the moment, calculations of neutron matter using effective field theory Hamiltonians are allowing us to estimate what is the error in the pressure at nuclear saturation density. Now, if you go to slightly higher densities, like twice nuclear saturation density, we discussed this earlier when we were talking about neutron matter calculations. The pressure in the uncertainty in the pressure increases, and it almost gets to the point where the low energy effective theory is breaking down. So beyond twice nuclear density, it's really hard to estimate errors in the calculation of the equation of state. So can we do something useful by just knowing the equation of state up to twice nuclear density and have this error bar? The answer turns out to be yes. Even though neutron stars explore much higher densities, there are two simple observations one can make to help extrapolate to these higher density regions. So the first observation one can make is that the radius of a neutron star is in fact very sensitive to the properties of matter shown in the green region. So if you really want to calculate what the radius of a 1.4 solar mass neutron star is, you really are interested in the behavior of the equation of state in the outer core of a neutron star. You're not very sensitive to the inner core properties. But on the other hand, if you want to know what the maximum mass of a neutron star is, then you're very sensitive to the inner core properties of the neutron star, or to the properties of matter at supranuclear densities. So if we want to extrapolate the equation of state to high density from twice nuclear density, we can ask, what is the maximum possible pressure that we can obtain at these higher densities? Because the speed of sound in any material has to be less than the speed of light, it puts an upper bound on the pressure. Remember that the speed of sound in any material is the derivative of the pressure with respect to the energy density. So the slope of the curve you can draw at higher densities in the equation of state diagram is limited. So there is no way to reach points higher than the dotted white line shown there, because if you want to reach those points, at some point you have to violate this physical principle that says that the speed of sound has to be less than the speed of light. So even though we don't know what sorts of matter can exist at these high densities, you can already put an upper bound on the pressure by just using causality as a constraint. Now, the fact I will discuss that we've seen neutron stars with masses similar to two solar masses. So you can ask, can I construct a neutron star with mass greater than two solar masses to be compatible with nature without by at the same time having very small pressure at high density? And the answer is no. So this lower boundary comes from the fact that any equation of state that you produce must have adequate pressure to support two solar masses. So just using calculations of neutron matter up to twice nuclear density, we can create boundaries at higher density based on these two observations. So any equation of state that is acceptable physically permissible, must lie in between these two lines. So one strategy could be, let's just parameterize the equation of state at higher densities by, say, taking 5 or 10 points between a few times 10 to the 14 grams per centimeter cube and a few times 10 to the 15 grams per centimeter cube, and then choose some arbitrary interpolation scheme. And then just try thousands or millions of equations of state that lie in between these two boundaries and see what sorts of neutron stars they produce. So what that implies is now we have an equation of state. Really, we have billions or millions of equations of state constructed. But as long as they satisfy those boundaries, you can construct neutron stars using a specific model. So what we did was we constructed neutron stars using neutron matter calculations up to twice nuclear density or just up to nuclear density, and saw what sorts of neutron stars they produced. And that's what's shown in this graph here. So if you just use the neutron matter equation of state up to nuclear density, then you see that it can produce neutron stars that are contained within the large space demarcated by the orange curve. If now you say, we believe the neutron matter equation of state up to twice nuclear density, the range of possible masses and radii decrease from to this green curve, where based on our best calculations at the moment, it appears that neutron stars have radii between about 9.5 kilometers and 12.5 kilometers. And the maximum mass of a neutron star is between 2 solar masses and 2.5 solar masses. So this is quite remarkable. What it's telling us is that even not knowing what the states of matter are at higher densities, we can already provide very stringent constraints on the neutron star mass radius by knowing the equation of state up to twice nuclear density. So one strategy then would be to start looking at observations and try to find out if, in fact, the neutron stars that we are observing are in this range between 9.5 and 12.5 kilometers, and if their maximum masses are somewhere in the range 2 to 2.5 solar masses. So now let's begin to look at what we have learned from observations. Before I go there, are there any questions about what I just discussed? Okay. So if there are no questions, the main point I wanted to make is that not knowing the equation of state in the core does not prevent us from making stringent constraints, from providing stringent constraints on the neutron star radii, because there are these two general principles that we can use, and that's an important point that you should remember. Now, what did we learn from observations? The most fascinating observations of neutron star masses are observations of very massive neutron stars. As we have discussed, making heavy neutron stars requires a lot of repulsive interactions between fermions in the neutron star core. And for that reason, the discovery of very massive neutron stars has played an important role in our understanding of dense matter. So when neutron stars are in binaries, we can, and when the neutron stars are both pulsars, there is a very well developed theory to study, to calculate the masses of the individual neutron stars by just observing the orbital motion of the two neutron stars. Sometimes these neutron stars can have a companion that is a white dwarf. Sometimes it can have a companion that's a regular star. And in some cases, we see relativistic effects. So effects that are coming due to either Shapiro time delay, when light passes in the presence of a companion object, there's a delay because it follows a geodesic that takes a little bit longer to get to us. So these sorts of effects allow us to measure very precisely the masses of both the objects in a binary system. So, for example, there is this pulsar J1714 -2230. That's a neutron star white dwarf binary, in which they measured a neutron star mass of 1.93. There are other neutron star binaries, neutron star white dwarf binaries, where they've measured larger masses. The largest mass measured to date is this pulsar MSP J0740, for which the mass of the neutron star is 2.17 solar masses with an error bar of about 0.1. So this clearly shows that there are neutron stars whose masses are greater than 2 solar masses. And so that was one of the constraints we used to kind of study the structure of neutron stars. The other constraint we'd like to have from observations is is a measurement of the neutron star radius. So because that's something that can also tell us about the equation of state. So in the past, neutron star radii were studied by looking at the X-ray emission from the surface of the neutron star. So if you have a black body emission from a spherical object, the amount of radiation you get depends on the surface area of the object, and by measuring the flux, and if you assume you know something about the spectrum of the radiation, then you can constrain the surface area of the emitting region, and that provides a constraint on the neutron star radius. However, the problem with trying to use X-rays to measure surface areas is that we don't understand the spectrum of X-ray emission from neutron stars very well. So if you made slightly different assumptions for the type of spectrum coming from a neutron star, for example, a neutron star probably has an atmosphere made of hydrogen. So if you have a hydrogen atmosphere on a neutron star, the hydrogen is going to absorb some wavelengths of light more efficiently than other wavelengths of light. So the emerging spectrum will look different from that of a black body. These small differences in spectra can lead to large systematic errors in the extraction of the neutron star radius. So this has been a problem for a long time, but theorists are very clever and inventive. They've tried to find ways around it, and for the best part, it looks like the X-ray observations of neutron stars from many neutron stars, which are shown in this plot in the lower right-hand side, suggest that the neutron star radii are probably in the range 10 to 12 kilometers, and you can see from the size of those extractions that both the mass and the radius of these objects is not very well constrained, but they're all compatible with being in the range 9 to 13 kilometers. And some of these observations also point to maybe a preferred range between 10 and 12 kilometers. So this is interesting because it is consistent with what we were predicting from theory based on low density calculations up to twice nuclear density. But the annoying part about these X-ray observations is that it was very hard to estimate the systematic errors associated with not knowing the X-ray spectrum. So all of that changed because we observed gravitational waves, and as I shall discuss, gravitational waves provide a new and more promising approach to determining the neutron star radius. So let me begin by discussing some very simple aspects of gravitational wave radiation from neutron star binaries. We know from general relativity that whenever you have a fluctuating quadrupole moment, mass quadrupole moment, which is denoted by the symbol ij, I sub ij, then it will produce some gravitational waves, and these gravitational waves are perturbations of the space-time metric h, and you can calculate what is the fluctuating quadrupole moment of a rotating binary of two neutron stars orbiting each other. And you'll find that the rate of change of the quadrupole moment is proportional to the mass of the objects. It's proportional to the radius of the object squared. So the mr squared is basically the effect of the quadrupole, and you have f is the frequency of the orbit, and then you can use Kepler's law to relate the radius of this orbit to the mass of the objects involved, and you will find that the amount of radiation that you get from a binary source goes as mass to the 5/3 power and frequency to the 2/3 power. So you do this calculation for a binary system, and you estimate what would the strain or what would the change in the space-time metric be at Earth, on the Earth, if you had a binary neutron star at some cosmological distance of, say, 100 megaparsecs. So, these are very rare events. So you have to see a very large number of galaxies to be able to detect enough events every year. So that's why typical distances for observing neutron star mergers is not measured on kiloparsec scales, which is the scale of our galaxy, but it's measured on 100 megaparsec scales. It's the scale at which you start beginning to seeing thousands or hundreds of thousands of galaxies. So at 100 megaparsecs, if two neutron stars merge, they will produce a change in the space-time metric of order 10 to the minus 23. So that's remarkable that there are instruments like LIGO that can measure such small strains. And I'm sure you've heard lectures on this or some colloquium on this, talking about the amazing detection of gravitational waves from a neutron star merger, demonstrating that in fact these instruments can see such incredibly small changes in the path length of lasers. So I'm not going to go into the details of the detection. Just mention that this detection has already occurred, and we think that the detection rate in the future is going to improve. You could have on anywhere between 1 detection a year to as many as 50 detections a year, based on our current understanding of merger rates. So the first detection was amazing because it was a very close by event. It was an event that occurred at 40 megaparsecs. So it's very, very rare to see events that are that close by. But we got lucky. Our very first event was a very nearby neutron star binary, and so what's shown on the right panel is the strain that was measured as a function of frequency and time. So these are just power spectra of the detector response. And when you see large power, it's shown as in green. And so the color code is blue is low power, green is high power. And you can see that, of course, there's a lot of noise because they're trying to measure a very small strain. But there's a very clear signature where the frequency increases as a function of time. The two neutron stars collide at time t equals 0. And so what happens is as the neutron stars approach each other, the frequency increases because as the radius gets smaller, the neutron stars spin around each other much faster. So this very characteristic increase in frequency as a function of time is proof that you're actually seeing a neutron star merger. And this neutron star merger has enough information in its waveform to extract certain source parameters. So the LIGO collaboration was able to extract the individual masses of the two neutron stars involved in this in the first merger. You can see that the error in the masses is moderate, but there are other quantities, like for example the chirp mass, which is given in the second line there, which is proportional to m1, m2 to the 3/2 power, divided by m1, m2 to the 1/5 power. You can see that combination of masses is extracted very accurately from the data. And because that is the combination of masses, that tells you how quickly the frequency increases as a function of time. So just the shape of this curve that you're seeing on the right-hand side is accurate enough to extract a specific combination of masses to the fourth or to the third decimal point. You can also extract the total mass of the two neutron stars in the system to good accuracy, in this case to the second decimal point. We are interested in the equation of state, so we are not very impressed by the fact that they can measure masses accurately, because we've already measured masses using other methods, and we've seen that the most interesting mass information comes from the very massive stars. So unless LIGO can measure masses of very high mass stars, it doesn't really help us with constraining the equation of state. However, LIGO, it turns out, can also measure the size of the neutron star, and the physics behind that is very simple, and let me describe that briefly. So if you have two neutron stars that are very close by, the tidal forces from one of the neutron stars will deform the second neutron star. So the tidal force on, say, the object 1 due to object 2 produces a quadrupole moment on object 1. So if the orbit between the two neutron stars becomes comparable to the radius of the neutron star, these tidal forces become very important. So there are two quantities that are relevant in the analysis of tidal deformation. One is called the quadrupole deformation, which is denoted by this function q, and the second quantity is the tidal force itself, which depends on the second derivative of the gravitational potential at the star at object 1 due to object 2. The proportionality, the constant between the amount of quadrupole you produce for a given tidal field, is called the tidal deformability of the neutron star. So this is something that all of us are familiar with. For example, when we study properties of atoms or nuclei, we think about things like the dipole polarizability. If you apply an electric field, how much of a dipole does it produce in a nucleus or in an atom? So that in the same way, this is a tidal deformability. The tidal deformability, you can think of it as the quadrupole polarizability of a neutron star. So it's a fundamental property of a neutron star, just like the mass and the radius of a neutron star are. So the tidal deformability is telling us something about the structure of the neutron star. And because the tidal deformations act on these two objects, what happens is that the rate of inspiral, so the two neutron stars are orbiting each other, the orbital frequency changes with time because it radiates gravitational waves. But when you have a tidal deformation, it changes the rate of change of this rotation frequency. That's because you're now moving energy from the orbital motion into the tidal deformation of the neutron star. So what it does is it actually speeds up the inspiral of the two neutron stars because of these quadrupolar deformations. And you can calculate in general relativity how the rotational phase of the two inspiraling neutron stars change when you have a finite tidal deformation. So, just to contrast this, if you had black holes instead of neutron stars, black holes cannot be tidally deformed, and in that case, the tidal deformation doesn't occur, and so the rate of coalescence is not changed. But in neutron stars, because they have a finite tidal deformability, you find that the larger the tidal deformability, the larger is the change in the rotational phase as a function of time. So this parameter, lambda tilde, which is the combination of the two tidal deformabilities of the two neutron stars involved in the merger, is defined in this line below. It's a dimensionless measure of how much tidal deformation is occurring in the system. So the other parameters that are in this equation here are V is the velocity of the two neutron stars that are merging, M is the total mass of the two neutron stars, mu is the reduced mass of the object, and this lambda tilde is this dimensionless tidal deformability. Now, the important observation is that the tidal deformability is a very strong function of the neutron star radius. So the bigger the neutron star is, the larger is its tidal deformability. So this dimensionless measure of the tidal deformability, capital lambda, is related to small lambda, which is a dimensionful measure that appeared in the equation above, divided by mass to the fifth power. And as I mentioned, the tidal deformability scales as the radius to the fifth power. So the bigger the neutron star, even small changes in the radius of a neutron star lead to very large changes in the tidal deformability of neutron stars. So this can be used, and it has been used to constrain the radius of neutron stars, because you can actually study the rotational phase of two neutron stars as they inspiral by observing the gravitational waves. So to kind of give you a clear picture of what happens, imagine that you have two neutron stars that are denoted in this figure by the green dashed curve, and you compare that to the merger of two black holes. And as I said before, the black holes don't have a tidal deformability, whereas the neutron stars have a tidal deformability. And in this particular plot, we've used specific values for the tidal deformability that we'll come back and discuss later. But it illustrates that when you have tidal deformation, the two neutron stars merge much faster than two black holes with the same mass. And you can see that in the last few cycles, which is the inset in the figure, you can see that there is a clear off shift between the green lines and the black lines, and the green lines clearly show that the two objects merge faster than the two black holes shown in black. So this offset, or this increase in frequency with time, can be measured for close by neutron star mergers. And from these measurements, you can extract the tidal deformability of neutron stars. So this is what was done. There's been many recent articles over the last 2 years trying to do the best job possible to extract this tidal deformability, and the results from one of the most recent analysis is shown in this figure here, where on the y-axis we show the radius of the neutron star, and on the x-axis the favored value of lambda tilde from this first observation of neutron star merger called GW170817. So the extractions clearly suggest that the data favors lambda tilde values of order 220 to 250. It depends on many details. It depends on, for example, our understanding of the neutron star population, because we don't quite know the individual masses of the two neutron stars very accurately. But the main conclusion one can draw from all of these analyses is that the tidal deformation of neutron stars is very small, which implies that the radius must be less than 13 kilometers. So this is a very robust insight, because this doesn't depend on systematic errors that were problematic in the analysis of X-ray extractions of neutron star radius. This just depends on a general relativity being correct, and very robust assumptions about the waveforms that go into analyzing the gravitational wave data. So the bottom line is the data suggests now that the radius of neutron stars has to be much less than 13 kilometers. More detailed analysis actually suggests that the radius of a neutron star is probably closer between 11 and 12 kilometers. And also one can do a calculation to show that the existence of two solar mass neutron stars implies that the radius of a neutron star must be greater than 9 kilometers. So between the observations and a stringent theory constraint, we now believe that neutron star radii are certainly in this range, greater than 9 kilometers and less than about 12 kilometers. Okay, so are there any questions about this part of the talk? Yes, please go ahead. Can you please speak up a little bit? The tidal deformability is deduced from the gravitational wave observations. Can you please repeat? I'm unable to hear you very well. Yes, now I can hear you clearly. Yes. Yes. Yeah. So I think I understand your question. You can measure in principle the radius of a neutron star directly if we measure X-rays and we know the spectrum, and we can measure the tidal deformability if we have gravitational waves. Now, of course, we will not be able to do that measurement for the same object because the X-ray observations are only for neutron stars in our own galaxy. And the gravitational wave observations are usually for objects that are very far away, and we don't have any X-ray information about those objects. But if we believe that all neutron stars are similar or have roughly the same properties for a given mass, then you can use what you're suggesting. You can try to measure the radius of a certain mass star in our own galaxy using X-rays. And that's really what is going on right now. So people are trying to measure the radius of neutron stars using data from a new mission called NICER, where they try to analyze the X-ray emission from the surface, and then that is used together with the gravitational wave data to see if they're both compatible. Right. Yes, I agree. So there is a measurement both from X-rays and from NICER, and they're also suggesting radii in the range 12 plus or minus 1 kilometer, and that is completely consistent with the gravitational wave data. And the reason it's robust is because the gravitational wave analysis doesn't depend on a lot of the complicated astrophysics associated with X-ray radiation. It's more robust. Yeah, please go ahead. Hi. Yeah. Okay. Yes. Absolutely. Right. That's exactly the point. So for black holes, there is no internal property other than mass, spin, and charge that defines the black hole in general relativity. No, this tidal deformability is a property of the compact object. It doesn't depend on its history. So if on the slide, you see that there is this relationship between the tidal deformability and the radius of the object. There is a parameter K2 that appears there on this slide at the very bottom. It is it is an exact relation where K2 is a function of the compactness. So K2 is called the tidal love number. When the compactness approaches the black hole compactness, K2 goes to zero. And that's why the black hole tidal deformability is zero. But for any other object, K2 depends just on how matter is distributed inside the star. Yes, exactly. Yeah. Okay. So this is something that's very exciting because this is likely a question we can address with observations. So when two neutron stars merge, they will either produce a hypermassive neutron star or a black hole. Uh, while current generation gravitational wave detectors cannot tell us what happened to the merged object because what happens after they merge is usually very high frequency. So we can see the two objects coming together and merging, but after they actually come together and merge, the frequency of the oscillations is too high for terrestrial detectors to determine the fate of the merger. However, the electromagnetic radiation from the merger depends very sensitively on whether you keep a neutron star alive for a long time after the merger or it immediately collapses to a black hole. So we are using electromagnetic observations of neutron star mergers to learn about the fate of a neutron star merger. So if the equation of state is very stiff, if it can support a three solar mass neutron star, then this particular merger should have produced a stable neutron star. And if you produce a stable neutron star, it's a very hot object that survives for a long time and it radiates lots of X-rays and it emits a lot of other gamma ray emission that should be detected. So we know already from the first neutron star merger that very likely the two objects live together as a merged hypermassive neutron star for a short period of time and then collapsed into a black hole. So we can rule out the existence of a stable neutron star in this case because we have been observing the electromagnetic radiation. It has important implications because if we are able to make black holes in the range 3 to 5 solar masses, those black holes must be made in this through this scenario. This would be one scenario to make those sorts of black holes, in addition to core collapse supernova. Yeah, okay. Let's make a break. I think this is a good time to break. I would actually prefer to address more questions than to keep lecturing because it's hard to know what is resonating with the students. So I appreciate the questions. Please ask many more questions, even if I don't finish my lecture. That's not important. It's more important that you ask questions. Yeah, let's make a break. We'll have a 10-minute break and we'll come back. Okay, very good. Okay. All right. So in the last session, let's kind of discuss what the implications of these observations are. If you remember from a few slides ago, I mentioned that if you observe small radii and large maximum masses, then it implies that the pressure must change very rapidly with energy density at some point in the neutron star core. So this has a very important implication for high density matter. So for example, the speed of sound in matter is related, the square of the speed of sound in matter is related to the derivative of the pressure with respect to the energy density. So if the pressure changes very quickly with energy density anywhere in the neutron star, that means that the speed of sound has to be very large. Now, it turns out we can calculate the speed of sound at low density using the neutron matter equation of state. We discussed how to calculate the energy and pressure, and so we can take those derivatives to calculate what the pressure is at very low density. So what we are seeing on this in this plot is a function, is the plot of the speed of sound squared in units of the speed of light squared as a function of the density, the baryon density. So at low baryon density, you can calculate neutron matter using nuclear interactions and effective field theory methods, and you find that the speed of sound is very small at low density. So if you only believe the calculation up to about twice nuclear density, you can see that the speed of sound is very small compared to 1/3 even at twice nuclear density. On the other hand, if you go to very high density, where the interactions between quarks become perturbative, that's the region where perturbative QCD works. And in that region, you can also calculate the speed of sound. And in that region where you calculate the speed of sound, you find that at asymptotic densities, the speed of sound is 1/3. And it turns out that quarks have attractive interactions between them. And so the leading corrections to the speed of sound actually lower the speed of sound compared to 1/3. So at very high density, the speed of sound is 1/3, and it's decreasing as you go from very high density down to more moderate densities. And at neutron matter, the speed of sound is increasing. So there are two possibilities for what happens in nature. One possibility is shown by the red curve, where the speed of sound increases monotonically from what we calculate at low density to its maximum value of 1/3, which is what happens in perturbative QCD. A second option is, of course, that the speed of sound increases very rapidly, goes to a value that's greater than 1/3, and then maybe through phase transitions or strongly correlated quark systems, the speed of sound decreases and then matches on to perturbative QCD. So what observations have taught us is that the simple monotonic increase of the speed of sound is no longer a viable option. And the reason for this is because it's not possible to make neutron stars that have a small radius and a large maximum mass if you have the red curve. So this is a very important insight that we were able to deduce from just observations, because the neutron stars certainly need a region where the speed of sound is rising very rapidly and very likely exceeds 1/3. And if that happens, we know that at some higher density, we need a transition of some sort to change this behavior and turn it around and bring it back to smaller values. So one robust conclusion of relevance to high density matter is this non-monotonic behavior of the speed of sound. But unfortunately, it turns out getting this very rapid increase in the speed of sound and a change in behavior poses very significant challenges to our understanding of high density matter, especially matter in which you have phase transitions. So now let's talk about what is generically possible at high density when you have new degrees of freedom. What happens to matter at densities greater than twice nuclear density? So there are other baryons that are a little bit heavier than the nucleon called hyperons. These baryons we know will begin to appear in dense matter when the chemical potential of baryon number is larger than the energy required to put a single heavier baryon into the system. So when you analyze the states of matter as a function of chemical potential, the threshold for the appearance of new particles is when the chemical potential exceeds the rest mass of the particle. So what's plotted in this figure is the baryon chemical potential as a function of density. Now, baryons can come with different charges. So a neutral baryon just couples to the neutron chemical potential. A negatively charged baryon couples to the neutron plus electron chemical potential, and a positively charged baryon couples to the neutron minus the electron chemical potential. If you remember, in the first lecture, we discussed how to write down chemical potentials for a given species in chemical equilibrium, and it just depended on the baryon number and the electric charge. And so these chemical potentials for different baryons with different charge just follows from those relations we derived earlier. So for example, if we want to ask at what density does the lambda baryon appear in dense matter, then the mass of the lambda baryon is shown by the black dashed curve. And when it intersects the neutron chemical potential shown by the solid black curve, at that point, you expect there to be enough energy in dense matter to produce lambda particles. If you want to ask what happens to a sigma minus particle, now the sigma minus is sourced both by the neutron chemical potential and the electron chemical potential. Because both of those values are increasing with density, it turns out that the sigma minus would, even though it's heavier than the lambda, the sigma minus is favored to appear at lower densities than the lambda particle. So if there were no interactions between hyperons and nucleons, then this would be the picture, because we would expect lambda particles and sigma minus particles to become very important degrees of freedom in the neutron star. So the only way in which you can prevent the appearance of hyperons in dense matter is if the interactions that they feel with nucleons is largely repulsive. Now, the problem with having hyperons in dense matter is because these are heavier baryons, and when they appear, they have lower momenta compared to the nucleons. So just on that simple observation, we can conclude that the appearance of lambda particles or any hyperon will lower the pressure. And we just discussed that what we want at higher density is some source of higher pressure, not some source of lower pressure. So we can already anticipate that there will be a problem with hyperons if we want to put them inside neutron stars. So the only way we can prevent this is by understanding hyperon-nucleon interactions, which may give us a mechanism to prevent the appearance of hyperons, and in that way ensure that the pressure doesn't decrease with increasing density. So for a long time, people had studied hyperons in neutron stars using the two-body interaction between a hyperon and a nucleon. And it turns out that the two-body interaction between a hyperon and a nucleon, especially the lambda hyperon and nucleons, is attractive. So that's catastrophic, because that would mean that the lambda particles would appear in neutron stars at fairly low density if you just had two-body interactions. So there are lots of recent calculations that have tried to include both 2 and 3 particle interactions in dense matter to study whether or not hyperons appear. So on the left panel is a calculation, basically a quantum Monte Carlo calculation of neutron matter containing lambda particles. And what one sees is that if you just have lambda neutron interaction, that interaction is attractive at low density, and for that reason, the lambda particles appear very early in dense matter. So you can see the density at which the lambda particle appears if you just have two particle interactions in the inset. That appears at about 0.25 Fermi to the -3. So that's less than twice nuclear density. And if you now allow for repulsive interactions between lambda particles and neutrons coming from the three-body interaction, then you can start pushing the threshold density to larger values, because now the energy needed to put a single lambda particle into dense neutron matter is larger because of all those repulsive interactions with the neutrons. And so as expected, you push the lambda threshold to larger values. Now, this has a significant impact on the mass radius curve. So that's what's shown on the right panel. So in the right panel, you can see that if you had no three-body interactions, that's shown by the red curve, then the maximum mass of a neutron star you can produce is now even less than about 0.6 solar masses. So this is catastrophic. So we know that lambdas cannot be present in a neutron star with the densities that is predicted by the red model. If you delay the transition density to slightly higher values shown by the blue curve by introducing a three-body force, you see that it's pushed to slightly higher densities, but it's still problematic because it cannot produce two solar mass neutron stars. A third model is one in which you have a very strong three-body force that is basically put in by hand to try and make hyperons appear at very, very high density so that the two solar mass constraint is still obeyed. So the maximum mass can be made to be larger than two solar masses by cooking up an interaction that is very repulsive so that lambdas don't appear. The problem, while this analysis gives us some insight into what is going on, it doesn't give us a robust explanation, because at these high densities, there is no hierarchy of two-body forces and three-body forces. There is no systematic way in which we can understand why hyperons do not appear at 3 times nuclear density, because at these densities, we don't have a theory in which the two-body interaction is less than the three-body interaction is less than the four-body interaction. So perhaps the more reasonable approach to understanding what happens, whether or not hyperons are present in the neutron star, is to say by the time hyperons are favored, the density is so large that the quark degrees of freedom in the nucleon becomes important. So you could say before hyperons appear, we expect that some form of quark matter may be favored, and that form of quark matter, once the quark matter emerges, perhaps hyperons are no longer a puzzle to include, but in any case, there should be some mechanism that prevents these hyperons from appearing in large quantities in the neutron star. And without it, we will not be able to explain the existence of two solar mass neutron stars. Yeah. Okay. Yeah, no, I appreciate that. Yeah, I think that remains a possible explanation for how one can have very small. Yeah, that's right. So that is exactly what this calculation that I'm showing also is doing, except for neutron matter. Okay. So the comment I made was that the description of interactions between baryons at high densities is not a well-defined problem because there is no hierarchy of many body forces, and that is probably giving us a pause to think about including quark degrees of freedom in some systematic way when you go to these higher densities. Now, another possibility that you should be aware of that was considered in the past is the appearance of bosons. There are negatively charged bosons in the hadron spectrum. The pi minus is an example. The K minus is an example. And we know, again, with the simple analysis, when you increase density in a neutron star, the chemical potential for neutrons increases, but the chemical potential for electrons, which are negatively charged objects, also increases. So whenever you have a object like a pion or a kaon with negative charge, when the electron chemical potential is larger than the rest mass of a pion in the medium, which is denoted by m star here, which just means that the medium can provide corrections to the mass of the particle through interactions, then that boson will condense. And at zero temperature, it will form a Bose-Einstein condensate. So it basically has zero pressure, and it has the same problems of the hyperons in that it lowers the pressure of matter dramatically compared to the gas of neutrons and protons, and that also is at odds with the two solar mass observations. So again, we need to find a physical mechanism by which the pion condensation can be prevented, because if pion condensation happens and there are lots of pions, it produces neutron stars with very small maximum mass. Kaons are much heavier, but we know that the kaon nucleon interaction is attractive. The pion nucleon interaction is repulsive at low energy, so maybe that repulsion is adequate to prevent pion condensation. This is also not fully understood. This is an active area of research. But with the kaons, we have to understand how much attraction is needed to provide kaon condensation at relevant densities. So there are different models for calculating the interaction energy of kaons with nucleons, and based on different approximations, you can get a transition to matter-containing kaons either at around 4 times nuclear density or at much higher densities like 6 times nuclear density. Again, these suffer from the same problems that we are trying to describe interactions between hadrons and mesons at very high density where there is no framework to organize the calculation. So hopefully, these are things that people will figure out how to address in the future more when we understand how to account for the quark degrees of freedom inside these objects at these high densities. So that just means that we have to discuss about 2 or 3 times nuclear density. We really have to start thinking about the quarks as important degrees of freedom, and a very simple model that has been used in the study of quark matter at high density is called the quark bag model. And this quark bag model provides the simplest explanation for confinement and deconfinement phase transition. Basically, the idea, which was proposed in the mid-1970s by people at MIT, Chodos, Bob Jaffe, and others, was to realize that the QCD vacuum is non-trivial, because the QCD vacuum has these strongly interacting particles. It's got the gluons, and the gluons are strongly coupled, so they condense and they give rise to an expectation value for this gluon field operators. So in the first line, there's an expression for the stress energy, the diagonal components of the stress energy tensor of the vacuum. This is just quark anti-quark pairs and gluons in the QCD vacuum, and you find that there is a finite contribution from the particles in the vacuum, and this finite contribution is called the bag constant. So the idea of the bag model is to say, why not think about nucleons as little holes in this non-perturbative vacuum in which you fill in quarks. So you have a non-perturbative vacuum everywhere. If you want to make a nucleon, you take 3 quarks, as shown in this picture, an up quark and 2 down quarks make a neutron, and you make a hole in the vacuum where this vacuum energy is expelled. So the energy associated with expelling this vacuum energy produces the mass of the nucleon, and the pressure produced by these 3 quarks contained in a very small volume pushes against the vacuum. So this is a simple model. Its connection to QCD is very tenuous, but it provides us a framework to think about the transition from nuclear matter to quark matter. So in this model, because the bag contribution is a vacuum contribution, the pressure of matter containing some finite density of quarks with Fermi momenta denoted by Kf is given in the expression on the right-hand side, where I write the expression for the pressure in the bag model as a function of the 3 quark chemical potentials, the up quark chemical potential, the down quark chemical potential, and the strange quark chemical potential. So if you're at high density, you expect to have all 3 flavors of quarks, up quarks, down quarks, and strange quarks, and each of those quarks will have their own Fermi surface, an up quark Fermi surface, down quark Fermi surface, and strange quark Fermi surface, and these quarks are all in beta equilibrium, and you require them to be electrically neutral. And once you know that, you would know all the individual concentrations of the quarks. So you will have the Fermi momenta for all the 3 quarks at a given baryon density. So the pressure as a function of chemical potential, now this is the quark chemical potential, and the quark chemical potential is defined to be 1/3 of the baryon number chemical potential, because they carry 1/3 baryon number each. And as you may remember from our discussion of thermodynamics, at 0 temperature and finite chemical potential, the state that has the largest pressure is the state that is favored. So the free energy is minus the pressure. So the state that has large pressure is the ground state of matter. So the nuclear matter equation of state is shown in the black curve. So if you use a typical nuclear equation of state, this is how the pressure changes as a function of chemical potential. Now, if you take a bag model, there is still this unknown coefficient associated with the vacuum energy of QCD, which is denoted by B. And if you choose a value of 200, which is favored by phenomenology, then you see that the phase transition happens at a chemical potential of order a little larger than 400 MeV. But if you choose a value that is a little bit smaller, if the bag energy is a little bit smaller, you can actually find interesting solutions in which the nuclear matter phase is never favored and the quark matter phase is favored at all values of the chemical potential. So this is a very exotic scenario in which nuclear matter is only metastable. Somehow, if you were able to supply nuclear matter with enough strangeness, then it would become more stable. It would have a lower energy than nuclear matter. And that form of matter is called stable strange quark matter. And for many years, this was a very exciting suggestion, because if this were true, then there would be, in addition to neutron stars, there would be a new class of stars made entirely of this stable strange quark matter, where matter would be composed of strangeness and quarks, even at very low density. So even in the outer core of the neutron star, you would end up having this very exotic matter. Now, I will not have time to talk about this. This is an extreme possibility, and there are observational hints suggesting that most neutron stars are not stable strange quark stars, and there's a lot of observational evidence for the existence of a nuclear crust and a nuclear outer core that I will not discuss. But I just want you to be aware that there is this extreme possibility of having a different class of matter other than nuclear matter. In the more reasonable range of parameters, one finds that there could be a phase transition from nuclear matter to matter containing quarks at high density. And because these intersections occur at an angle, they're not. It implies that this phase transition is first order. So this intersection between two states of matter, say the green curve and the black curve, implies that there's a first order phase transition from nuclear matter to quark matter at the point of the intersection. Now, you can also say, well, let's try to do something better. Let's try to calculate QCD using perturbation theory, even though the So when we got cut off, we were talking about including correlations between quarks, because the bag model was too simple. It just had non-interacting quarks in a cavity. And now we want to actually account for interactions between quarks. And these interactions we know are very important because they account for things that we know occur in nature. For sure, chiral symmetry breaking is something we know is present in the QCD vacuum, and that arises due to quark anti-quark correlations. And at high density, we expect the correlations between quarks to become more important. And a simple model that can account for both of these effects is called the Nambu-Yono-Lasinio model. And if you look at the expression for the Lagrange density given in the equation, the first equation, you see the familiar kinetic term for quarks with a mass small m, and the mass is the bare mass of the quarks. And then you have a 4 fermion coupling. This is very much like the contact interaction we introduced in the effective field theory for describing interactions between nucleons at short distances. This is an interaction between quarks at short distances, and there is one coefficient g, which determines the strength of these interactions. And there are various Lorentz structures for these interactions, because you know from your quantum mechanics, relativistic quantum mechanics class, that the operators that you can write, you can have quark bilinears of many kinds. You can write psi bar psi, you can write psi bar gamma mu psi, and so on. And so you pick the operators in such a way to represent the interaction in different channels. And there are variants of this. So this was the original, the first line up there is the original Lagrangian written down by Nambu-Yono and Lasinio. There are extensions in which you write additional terms where in addition to the gamma 5 tau, and tau is the isospin, is the matrix in isospin space, you can write variants of it. Bottom line is, it's a way of including interactions in different channels of quarks. So this acts in color space and also in flavor space. The color indices are suppressed, but this also tells you that different colors of quarks interact with different strengths. So before we talk about the interaction of relativistic particles, I want to mention something that is very robust and very common. It is the phenomenon known as Cooper pairing. And this is exhibited even by the simplest Hamiltonian or simplest Lagrangian you can write down for fermions. So if you were to write down the interaction between two non-relativistic particles, like say neutrons or electrons in a metal, you will find that there is a short distance interaction term you can write between these fermions. And whenever the interaction is attractive, stable at zero temperature and no interactions, becomes unstable. And the reason it becomes unstable is because this interaction, no matter how small the interaction is, it is capable of forming pairs of fermions called Cooper pairs. And the way we mathematically describe these Cooper pairs is by assigning an expectation value for not the density. The density we know has an expectation value. The density is A dagger A, but these other operators that are pairs of operators A or A dagger, those are operators that produce or annihilate a pair of fermions in the vacuum. So when they have an expectation value, it means that they have there is a condensation of Cooper pairs in the vacuum. And this happens for arbitrarily small coupling G. So it is almost any fermionic system, if you take it to low enough temperature, will form a Cooper pair at the Fermi surface. It has two important consequences for the state of matter. The first consequence is that if you take a Fermi system and you give it a small amount of energy, you can always take a fermion at the Fermi surface and promote it to a higher energy state. So a simple Fermi system has no gap in the excitation. So if I give energy to a Fermi system, even a small amount of energy, it is able to accept that energy because there are excitations available to it. So when you form Cooper pairs, the energy for excitation of fermions develops a gap. So you have to give it a finite energy to actually produce an excitation. So at the bottom, you have the energy momentum relationship, the dispersion relation for fermions, and you see that there is a finite value even at the Fermi surface where the energy is where the momentum is equal to the Fermi momentum. So this is the first consequence of Cooper pairing. The second consequence of Cooper pairing can be seen by noticing that this pairing field delta is like an order parameter, but it's a complex order parameter for this phase transition. So when you have interactions, the ground state wants to have a finite expectation value for this delta. But delta is a complex field, so the magnitude of delta is what enters the energy. There's the phase of this delta. So if I make a plot of the free energy of this Fermi system as a function of this order parameter delta, it has this Mexican hat potential that you're familiar with. And that's what's shown in this figure here. So you can think about what happens as you move along the rim of the hat, the increasing values of delta, you will find that the free energy decreases and there's a minimum. But there is a orthogonal direction which is associated with the phase. And when you move in the orthogonal direction, there is no change in energy. So the phase, changing the phase of this condensate costs no energy, and that excitation of the phase is called the Goldstone boson. And so whenever you have superfluidity, the two important consequences are, one, you have no gapless fermionic excitations, and the second consequence is that you actually have a new excitation, which is a bosonic excitation associated with the phase of this fermion condensate. So these are generic things, whether it's a non-relativistic system or a relativistic system. This is always a property of any Fermi system with attractive interactions. So this, if we had a fourth lecture, we would have talked about how neutrons, which are non-relativistic particles in the neutron star crust, also have this pairing and they form a superfluid of neutron matter. But now let's come back to our discussion of quarks, because quarks also have attractive interactions at the Fermi surface, and they also have interactions between quarks and antiquarks. Are there any questions about this? I'm sure you've seen this before, but if you have any questions, I'm happy to address them. Okay. So in a relativistic system, there are two types of pairing that can occur. So now coming back to quarks, you can have quarks that pair with antiquarks because of interactions. So if you take the Nambu-Yonah-Lezenia model, you will find that the quark-antiquark interactions can be accounted for by just calculating the free quark propagator in the presence of other quarks in the systems and other antiquarks in the system. So the way we calculate this is to solve what's known as a Dyson equation, which just tells us how the propagation of a single quark is modified in the presence of antiquarks in the background. And the equation is depicted diagrammatically. Equation is given on the right hand side, and the way it's written is that the quark, when it's propagating in the presence of antiquarks, actually gets a correction to its mass term. And so the propagator on the right hand side is represented by this function s, and the integral is over all possible momenta of this intermediate state that the quark scatters from, and it produces a shift in the mass of the quark. Instead of having the bare mass small m, the quark now has a dressed mass capital M. So that dressed mass is what we identify with the constituent quark mass inside a nucleon, for example. And small m would be the bare quark mass. The bare quark masses we know in QCD are very small, and the constituent quark masses at low density are of the order of a few hundred MeV. So that means that this 4 fermion interaction in this model must create this large energy or the large mass that we see in the quarks. And this gap equation, which just solves for this propagation, tells us the relationship between the mass of the constituent quark and this 4 fermion coupling. So one way to fix the 4 fermion coupling would be to just fit to the constituent masses of quarks inside a nucleon. Now, the consequence of this sort of interaction is that it provides a finite expectation value for the operator Q bar Q. Just like the superconductivity provided a finite expectation value for A dagger in the non-relativistic Fermi system, in the relativistic Fermi system, this quark-anti-quark interaction produces a finite value for this. And the finite value is related to the difference between the constituent quark mass and the bare quark mass. Now, as you increase the density, because the quarks and the antiquarks are now separated by the Fermi surface, the interaction between quarks and antiquarks becomes suppressed as you increase the density of matter. So in the vacuum, there's no finite Fermi surface. So when you calculate this, when you do this integration, you don't have to worry about all the Pauli blocking of states between 0 and the Fermi momentum. So you get a large value. But as you go to higher densities, this integral is suppressed, and the constituent quark mass becomes smaller, and eventually it becomes equal to the bare quark mass. So one expectation is that as you increase density, we expect the chiral condensate, the Q bar Q condensate, to decrease because all of these states are occupied. All of these fermion states are occupied, and that affects the calculation of this Dyson equation. On the other hand, as you build up the Fermi surface, the effect that becomes relevant is pairing at the Fermi surface. So instead of having Q bar Q, you have a QQ. You have a condensate formed from quarks alone, 2 quarks at the Fermi surface, and that is represented in general by an expectation value for this operator, Q transpose, and this operator in the middle. This has some Dirac structure, it has some flavor, it has some color, and those are important. And the region and those quantum numbers will be determined by the nature of the interaction in that channel. So if there is a attractive interaction in some channel, let's say you have attractive interactions between up and down quarks, or between up and strange quarks, then that operator will tell you what is the type of isospin, color, or flavor structure that needs to be there. And typically the most important channel for pairing is the pairing of quarks with spin up with quarks with spin down. So if you assume that the most important pairing is between spin up and spin down quarks, which make spin 0 Cooper pairs, then in QCD, the most important quark pairing channels are depicted in this diagram here. And it turns out that the attraction is largest in the color antisymmetric color, in the color antisymmetric channel. In other words, we know quarks, at least the light quarks, come in 3 flavors and 3 colors. So you have basically 9 types of quarks you can write down. So you have 3 red quarks, up, down, and strange, 3 green, up, down, and strange green quarks, and so on. The lines that are shown in that figure show the channels where the attraction is the largest. So, for example, pairing between an up quark and a green up quark and a red down quark is very strong compared to the pairing between, say, 2 up quarks. So these are the channels that are going to produce the example. The consequence is that once pairing occurs, the quarks that are participating in pairing will have an energy spectrum that differs from that of a Fermi gas. So you start producing these energy gaps, delta, in the Fermi system. So if you had equal numbers of up, down, and strange quarks, then this pairing pattern will give rise to the ground state of matter. Now, the other condition that you need to have pairing is to make sure that the quarks that are pairing all have the same Fermi momentum. So if the up quarks and the down quarks have the same Fermi momentum, then they can pair. If the Fermi momenta are very different, then pairing becomes difficult, and pairing is usually disfavored. So there's a competition between these 2 effects, the separation between Fermi levels and the pairing that's trying to force both the Fermi levels to the same energy. So in dense matter, are the quark Fermi surfaces all the same? And the answer to that question is no, because we have certain conditions that have to be satisfied at high density. So if I just took nucleons at high density, there are a certain number of neutrons, there are a certain number of protons, and there could be a certain number of strange baryons. If I just make that go to high density, the number of up, down, and strange quarks will be different. So the 2 conditions that they have to satisfy, one is that they have to be in beta equilibrium. So turning an up quark into a down quark and back, that must satisfy the beta equilibrium relation. And when I count the total charge, the number of ups, the total number of positive charges should be equal to the total number of negative charges. So when you impose these conditions, you find that the down quarks are the most common quarks at high density. The up quarks are a little bit less common. Their Fermi level is smaller by this factor ms squared over 4 mu. The reason for all of these differences is because the strange quark is more massive than the up and down quarks. If all the quarks had the same mass, then there would be no reason to have a separation between the up, down, and strange quark Fermi momenta. So the separation between Fermi momenta is measured in units of ms squared over 4 mu. It turns out that if the pairing energy is larger than ms squared over 4 mu, then the ground state of the system contains equal numbers of up, down, and strange quarks, even though the strange quarks are heavier. Because you can gain energy by pairing, you end up having equal numbers of up, down, and strange quarks, and in that situation, you don't need any electrons. So that state of matter is called color flavor locked matter, because color and flavor are locked into forming Cooper pairs through these connections that are shown in this diagram. In this state of matter, what happens is very interesting. If quark matter appears and it appears in this state, what is the consequence? The consequence, as we discussed, is that the excitations of quarks is very different. In this case, there are no electrons, so there are no free fermions to excite. The quarks are all gapped, so you always have to give a finite amount of energy to excite a quark. So what's shown in this figure is the energy for excitation of various particles. The other part that I haven't discussed is what are the symmetries of the state that you produced after pairing compared to the symmetries of the state that existed when you had no pairing. So whenever you have a phase transition, especially phase transitions like Cooper pairing phase transitions, it breaks some symmetries in the ground state. So if the Fermi gas ground state had certain symmetries, the superfluid state will have lesser symmetry because of this pairing pattern in the ground state. So in QCD, we know what are the symmetries when you don't have pairing, or in the ordinary state. The symmetries are denoted by chiral symmetry. That means that you can take all left-handed quarks and perform a rotation, or right-handed quarks and perform a rotation, and the state of the system doesn't change. You can take all quarks which carry baryon number and add a phase to it. That doesn't change the energy, and that symmetry is called U1 baryon number symmetry. And there is a color symmetry associated with changing the phase associated with the gauge fields. And so all of these symmetries are obeyed in the Fermi gas state, but they're not obeyed in the superconducting state. In the superconducting state, those symmetries that remain are these symmetries which are written in the line below. So the U1 baryon number symmetry is broken, and chiral symmetry is broken. Now, the U1 baryon number symmetry and the chiral symmetry are called global symmetries associated with those symmetries. And that always leads to the production of Goldstone bosons. So we saw in the simple example of non-relativistic fermions pairing that there was a phase degree of freedom associated with a Goldstone excitation. So that same excitation exists also in quark matter because you've broken the baryon number symmetry. But in addition, there are a whole bunch of other symmetries broken associated with the chiral symmetry breaking, and that leads to more Goldstone bosons in this phase than in a one-component superfluid. So this state of matter, if it exists, has very different properties at finite energy, or from that of a Fermi gas. So a Fermi gas would have gapless excitations at the Fermi surface. This state of matter is radically different. It has no Fermi excitations. It's just got a lot of Goldstone bosons that you can excite. Okay, so I should probably stop here and take some questions, because what we've discussed possible states of matter at high density, hyperons, kaons, quarks, and in the quark phase, it seems that these correlations that produce pairing is very important. And the way these lectures were designed, I was going to take a break here and talk about something completely different, which we don't have time for anymore. So let's just break here, and you ask me questions about the high density phases that we discussed. Yes. So in the neutron superfluid, there is a Goldstone boson associated with the breaking. So there is a phonon of the neutron superfluid that is actually important in astrophysics, that exists in the neutron star crust, and it also exists in the neutron star core, outer core. There's one Goldstone boson. And the way you would recognize it is if you took neutron matter and you heated it up, you would find that the excitations in hot neutron matter at low temperature would all be Goldstone bosons. Yeah. Yeah, no. So the uncertainty in the theory is too large to exclude the possibility of their appearance in the core. What it depends on mostly is the size of the superconducting gap. If the gap due to pairing is of the order of 100 MeV, then if quark matter appears in neutron stars, it will most likely be in the CFL phase. If the gap is less than 100 MeV, if it's like 50 MeV, then what happens is that it is likely to be in some other state of matter in which some of the quarks pair, but not all of them. Because you can look at this figure here, when the gap is large compared to the strange quark mass divided by 4 mu, then CFL is robust. So in that case, we would say that if the neutron star contained quark matter and the gap was large enough, then the ground state of matter is given by color flavor law. But as soon as it becomes less than ms squared over 4 mu, then it becomes very complicated to analyze the phase diagram, because there are many other states of matter which are all very similar in energy with different pairing patterns that are possible, and we will not be able to distinguish between them. When you think about neutron proton matter with electrons, I only touched the surface in terms of the complexity of that phase. When you look at the excitations of a plasma containing neutrons, protons, and electrons, there are collective excitations in that phase, which are collective excitations which involve the oscillation of electrons and protons together, and that oscillation is a plasma oscillation, and that has important implications for transport of heat and transport properties of dense matter. So yes, you're absolutely right. There are other collective oscillations associated with electromagnetic charges fluctuating. And it turns out that these collective oscillations actually mix. So you can excite the electrons and protons, and because the protons interact with the neutrons, that oscillation mixes with the oscillation of neutrons, which is a superfluid mode. So the eigen states of collective excitations in neutron star core is a very interesting topic, where you have excitations that are mixtures of plasma excitations and neutron excitations. Yeah, yes, I will send you PDF versions, or I will send you a link to my Dropbox so you can download all four of the slides. I am, again, I'm sorry for not being there. This is not ideal. I appreciate your patience with the technical difficulties. Yeah. Yes, I hope all of you have a safe journey back home. Thank you for listening. Bye bye.